Welcome to part 2 of this discussion for chapter 19. So this part is mainly dealing with the problem of, solving some couple of problems. Problem 38 and problem 39. And as I said in the previous recording, problem 60 from this chapter. So I'm going to discuss these three problems. And I think I'm probably going to go in a little bit of detail about these problems. So problem 38, basically, if you look at it, so we're going to read the problem. So it shows you a diagram, PV diagram that is, and it says that you have 3¼ moles of an ideal helium, which is a monoatomic gas, by the way. And then it shows you in the diagram that it went from point A to point B to point C and then back to point C. The portion CA is an isothermal portion. That means it's at a constant temperature, which means the energy is not changing. So that's when you're reading problems like this one, try to take note of everything in here. So let's draw the graph first to see how things look like, okay? So in this problem, what I have in here, I have point, so we have from 0 to about 0.4. So let's draw the axis first. So this is a PV diagram. The volume changes, starts from a point A. So this is the starting point. And then, it doesn't say that specifically, I guess, but you can, this process, portion of the process from A to B is at constant pressure. So P is constant. PA is equal to PB. That's constant pressure. And then it goes to a point C at constant volume. So again, this process from F to point C is the same volume. In other words, VB is equal to VC. Okay? So that's basically, we can clearly see from this diagram, and that volume is actually given to be in the diagram in here, 0.04. Let me check the units in here. It's a cubic meters. So this is the volume in cubic meters. So it's in SI. Nice. Okay. The pressure in this point is given to be, in that point, PC is equal to 2, and the units are in Pascal. I mean, hundreds of thousands of pascals. PA times 10 to the power 5. So it's 2 times 10 to the power 5, basically Pascal. So that's nice. Okay, everything is given in SI. They say specifically, so the direction of the process is that we go expanding from VA, which is not given, by the way, to VB, which is equal to VC, by the way, because it's an isochoric process at constant volume. And then we go from C back to A at constant temperature. Okay, so this portion in here is an isothermal. This is an isobaric, and this is an isochoric. So we have 3 of the main processes that we discussed, 3 out of the 4 that we discussed earlier. By the way, if the pattern is any kind of arbitrary process, what I'm trying to say in here is that processes can be more complicated than this 4. It can be any path you like. So it could be a path like this one. So this is not any of the above. So you really need more details on those processes, okay? But at least the simple processes, namely the isobaric process, the isochoric process, the isothermal process, and now the adiabatic process, where there is no heat exchange, then in this case we know how to deal with them, and then hopefully we have easier problems down the road. So in this problem in here, that's all we're given. So we're given PC, we're given VB, which is now equal to VC, and then we don't know what PB is, we don't know what VA is. No, VA is actually given. So this volume is actually 0.01 cubic meter. Okay, they have the sig figs in here taken into account, okay? So this is also given. So this volume VA is given. So we have enough information to. So find the pressure of the helium at point A. So we need to find PA, basically. That's the question that we need to find. Once we find it, we actually know what PB is also. That's not asked, but we know what it is. So for that, we need to apply PV at point A. So PA VA equal to NR times the temperature at that point, A. Well, I know what VA is, it's given to me. I know what the number of moles also is given to be 3¼ moles. So that number is given. What else is given? That's all it's given. So I really need to know, I have N, I know what R is. I know what VA is. I don't know what PA is. I need to know what the temperature TA is. Because this process is an isothermal, this temperature is the same at point C. In other words, TA is equal to TC. So if I can find TC, I'm in business. So let's find TC. I know that in point C, I have PC times VC is equal to NRTC, which is the same thing as TA. So these two temperatures are the same. So if I find this expression, sub it in there, and I'm in business. So instead, because these two temperatures are the same, so I can write this expression as an as TA, and this is PC VC. So I can do the ratio of these two expressions, expression 1 and expression 2. And I will find that PA VA over PC VC, BC, is equal, the N cancels the N, the R cancels the R, the TA cancels the TA because it's the same temperature, is equal to 1. From here, I can find what this pressure at point PA, which is, by the way, I can clearly see it's also PB, it's the same pressure, is equal to, from this equation, PC VC over VA, or PC times VC over VA. So whatever PC was, which was 2 times 10 to the power 5 Pascal, times the ratio of the two volumes, so there is no need to convert anything to anything. So it's VC, which is 0.04, divided by VA, which is equal to 0.01. And this should be 4 over 1 times 2. So this is 8 times as much. So this pressure here is 2. This is 8 times as much. So this is 8 times 10 to the power 5 Pascal. Does this make sense? Of course it makes sense. This is higher pressure. At least from the graph, it looks like it's higher. But I know it's 4 times as much. So this is 8 times 10 to the power 5 Pascal. So that answers the first question. Okay. Always, when you're doing this kind of problems, analyze your results. See if it makes sense to you. Okay. At least graphically in here, it looks like the pressure is higher. Okay. And I did find it higher. If it was the same pressure or less, then I have a problem in solving this equation in here. Okay. Because we kept the temperature the same. The temperature did not change. And we lowered the volume. Remember, PV equal to nRT. If we made the volume less, the pressure better be higher. That's exactly what we found. I mean, probably you guys are not seeing it. The expression that I'm dealing with is PV equal to nRT. T is fixed because it's an isothermal process going from C to A, which means that if V is becoming smaller, it was 0.04, went to 0.01, that means it went 4 times less. The pressure has to increase 4 times more. Simple as that. Okay, so this really did not require a lot of algebra. We could have thought it and came up with the correct answer. Okay, so that's question A. Question B, find the temperature of the helium at points A, B, and C. Okay, I know the temperature as point A and C are the same. So I know TA is equal to TC, and we can use the ideal gas law, which said that TA is equal to TC is equal to PAVA over NR. Okay, PAVA over NR, and we have everything in this case. So PA is, the pressure at point A is 2 times 10 to the power 5 times the volume, which is 0.04, divided by N, the number of moles is 3.25, times R, which is 8.314. I'm gonna need this calculation, so I'm gonna pull a calculator quickly here and see how much temperature is, because I need to get something in here out of these numbers in here because I want to compare it to the second temperature. So let me quickly do the math in here. So I have 2 times 10 to the power 5, and the whole thing is multiplied by 0.04. I could have done this quickly without having to do these things in here. Divided by 3.25 times 8.314. The number of moles is very large, okay? So I found 296 Kelvin, okay? So the answer to this expression in here, 296, so that's the temperature in Kelvin, by the way. It's 296 Kelvin, or deduct from it 23, direct 273, 23 degrees Celsius, okay? However you want to write it, the same thing, okay? So we know what the temperature is, okay? Is it 23? Yeah, that's correct, okay? So it doesn't matter, it's 296 Kelvin. So we found the temperature at points A and C. How about the temperature in point B? In point B, what do we know? We know the pressure is PB, which is 8 times, is it 8? Yeah, 8 times 10 to the power 5 Pascal. We know also the volume, which is 0.04, okay? We know there's two things. And we want to find the temperature. So we're going to use the same expression here. So TB now, which is different than the other, it should be higher, by the way, because this is part of another isothermal that is sitting at a higher point in there. So let's find TB. So it's going to be PB times VA, times VC, VB, I'm sorry, divided by NR, okay? Okay, the volume is the same as VA. The pressure is 4 times as much. So we should find it 4 times as much. So it should be 4 times 296. So if you plug in all the numbers, because everything is the same, the volume in B is the same volume as C, which is 0.04. This expression in here is 4 times as much. It's not 2, it's 8. And everything else is the same. So we should find 4 times 296. Which is, how much is that? 4 times 296, which is 1184 Kelvin, or it's going to be a large, high temperature, extremely high, 911 degrees Celsius. This temperature is so high. I mean, you need super precautions to work with this thing. And a lot of materials melt at that temperature. Okay. So in other words, when you're doing these problems, part of the discussion is be careful with these numbers because sometimes they come up ridiculous numbers like this one. 911 degrees is very high. So if somebody does an experiment and finds a temperature, for example, of 7,000 degree Kelvin, you know that you're dealing with something that is hotter than the surface of the sun. So you have to be very careful with this number. So when you're doing these problems and discussing them, you really have to have an understanding of what's going on in here, okay? Okay, what's the question here? How much heat entered or left the helium during segment A, B, and then BC and CA? In each segment, did the heat enter or leave the gas? Okay. So the question is, in going from AB to BC, AB, how much heat it is. So we know we need to find CP now, and we need to find CV. This is a monoatomic gas, so this is 3/2 of an R. And this is just plus R to it, so it's a 1 plus, basically, so it's going to be 5/2 of an R. So we know what CV, we know what CP is. Because process going from AB, we need CP. For the process going from BC, we need CV. So this is the process BC, okay? So this is the process AB. And for the process going from back to C to A, we just need W and then make Q equal to minus W, basically. Because in this process, there is delta U is 0. There is no increase or change in the... so we can find all of this expression. So let's do that, okay? Because this one is at constant pressure, so Q is equal to NCP delta T, okay? And Cp is, so we're going to write it N times 5/2 of R times the change in temperature, which is basically Tb minus Ta. Okay, and this expression, so this process is going from AB, by the way, the heat from AB. So it's heat from A to B is N, which is 3.25, times 5/2 times 8.314 times the difference in temperature, which is, it has to be in Kelvin, okay? No, I'm sorry, the difference, it doesn't matter at this point. So it's going to be 1,184 minus 296. Plug in all the numbers, you'll find the energy in joule, the heat in joule. So I'm going to put these numbers in here quickly in my calculator. 3.25 times 5/2 times, okay, times 8.314 times, open parentheses, 1,184 minus 296, and this expression, if I'm careful enough with my numbers, 60,000 joules, basically 60K. It's a big, basically 60,000 joules. I mean 59,900 and something. Okay, kilojoules, 60,000 kilojoules. Okay, 59,985 point something. Okay, the question that you're going to be doing in here is verify my numbers. So this is the third question of this discussion in here. You need to check everything in here that I'm doing. Okay, so we found Q in the process going from point A to B. Okay, this portion. We need to find Q going down in here. Okay, remember the temperature is less than the temperature, Tc is less than Tb. So this Q is going to be negative. Actually, it's going to be extracted from the system. So while we're basically decompressing it, basically releasing the pressure, it was very high, now it's less at constant volume. So the system will cool down. Okay. So it's going to lose heat in that sense. Okay, so in here this is heat gain. So this 60,000 is added to the system. So this is a positive number. So let's do Q now from B to C. That is actually equal to, at constant volume, not at constant pressure, delta T. So I have 3.25 times 3/2 of R. Remember, 3/2 of R is 3 times 3.4. The final temperature is 296. The initial temperature is basically 1,184. And this number is easy to calculate, which is identical to the first number, except the first one was 5/2. This one is 3/2. So this number, I'm sorry, probably you guys are not. Hold on. So this number, the first one was 5/2. Everything is identical with the exception there was 5/2. This one is 3/5. So all I have to do is multiply the first number by 3 and divide it by 5. So Q for B to C is equal, the sign has flipped now. It's minus 3/5 times 60,000 kilojoules, or 60 kilojoules. That's all there is to it. So 3 times 6 is 18 divided by, so it's 180 divided by 5, which is 36,000 with a negative K, negative 36 kilojoules. Okay, please verify. So it's part of your task is to check the numbers that I'm doing in here. So at some point of the cycle, the system is getting heat, extracting heat basically from the hot source. So in here, we're taking heat from the hot source. And in this point in here, we're dumping heat. The system is dumping heat to the cold source. Okay? Okay, so that's QC. There is also another portion in here where we're compressing it in here. So we're making W in here is going to be positive in this case, because remember, the volume is negative times a negative, so it's going to be positive. So the work is negative. So this will add to that too. So there is another QC in here. So there is a QC2 and QC1. So we got a lot of heat initially from the hot source, which was 60,000 basically joules, and now we dump 36,000 in here, and QC2, how much it's going to be? Is it going to be the difference, or is it going to be more? We will see. It should be less than the difference of the two, because we ended up doing work in this portion in here. So part of it is actually gone to the work in here. So let's find QC2. QC2, as I said, has nothing to do but just finding W and going from so we're trying to find Q from C to A, by the way. And what I'm saying in here, it's equal to minus W. And we calculated that in lecture, which is just the positive in this case of NR T ln of V2, the final volume, which is VA, over the initial volume, which is VB. I'm sorry, VC. Okay, which is equal to VB, by the way. And this is going to be negative, of course, because the fact that this number is a quarter. So it's going to be NR, N, which is 3.25, R, which is equal to 8.314, times the temperature. The temperature is at point A, which is 296 Kelvin, times ln of 0.01 divided by 0.04. Okay, I need this number. I need this QCA. First of all, it's going to be negative because of this ln in here. Okay, and again, as I was saying, this is actually has to be negative because we're dumping heat in here. Okay, because the gas is being compressed, which means that we're doing work against it, which means that we're adding energy to the system via work, but no change in the total energy because this is an isothermal. The temperature is constant, so delta U is equal to 0 because delta U is equal to 0 and it's equal to Q plus W. So in this case, whatever we add to the energy of the system from the work must be lost to the heat in this case. And that is just the portion CA. Only from CA, not everywhere, okay? Not true everywhere. For this one, because CA is an isothermal process. Okay, so let's find the numbers in here because we need to get this number in here to see how much is that. So what do we have? We have 3.25 times 8.314 times 296 times ln of, I don't know if this expression, this is a proper way of doing ln on this calculator or not, divided by 0.04. Yep, it's negative 11,000 something, which is very close from negative 11K joules. Okay. As I was saying earlier, note that QCA plus QBC, which is equal to negative 11,000 kilojoules minus 36,000 kilojoules, is not equal to, at least in magnitude, to the QH, which was the process where we gained heat from the hot source from A to B, and that was 60,000 kilojoules. This one actually is equal to negative 47,000 kilojoules. In other words, there is a net heat that we're extracting it from the hot source. We took 60,000 kilojoules and we dumped from the stages, so basically, let me go back into the diagram here. So here, we took 60,000 kilojoules. Here, we dumped 36,000 kilojoules. Here, we dumped 11,000 kilojoules. So there is a net, take from the hot source, which is 60 minus 47K. So Q net, in this case, which is the difference between the two, QAB plus QCA plus QBC, and that is equal to 60 minus 47, which ends up to being 13,000 kilojoules. That, in my prediction, is how much work we're actually doing. Okay, so Let's continue with this questions in here. So we asked question, what is it, C, how much heat entered or left the head during. So the amount entered was 60,000 kilojoules. The amount left was 36 and 11 kilojoules. Okay, so that's how much heat basically was. By how much did the internal energy of the helium change from A to B, B to C, and C to A? Okay, how much energy? Okay, so we need to ask the question from C to A, from, what is it, the starting point in here? Let's do from A to B first. We want to know delta U. From B to A, B to C, we want to find delta U. And from C to A, we know the answer, it's 0, because it's an isothermal process. Okay? So that is equal to 0. From A to B, delta U is equal to the Q that we calculated from A to B, plus the work in here, from A to B. From B to C is equal to Q BC plus the work, but that's an isochoric process. Here, it's an isochoric process. So that's all there is to it. So delta U in this case went down by 36,000 kilojoules. Okay, here it's 0. So the energy in going from here, so this one, I'm not going to do a lot of calculations, but I know it's going to be also 36,000 kilojoules. Why? Because the energy is a conserved quantity. So if the entire cycle going from A back to A ends up with 0, and I have a negative in here, so I better have positive 36 kilojoules. I know this amount, Q to A to B, QA to B is 60,000 kilojoules, correct? A to B is 60,000 kilojoules. So I need to find this number, and I'm expecting this whole number to be 36,000 joules. So this number be just exactly the difference. This must be 13,000 kilojoules, okay? No, not 13, I'm sorry. 60 minus 36 is what? 24. So this must be 24 kilojoules, okay? With a negative number. So let's continue the discussion. So what we found is, in the process going from A to B, basically, remember that was a process at constant pressure, delta U, we found it to be equal. It's always the sum of the heat plus the work. But this process is for the cycle, for the process AB, which is a process at constant pressure. So this was equal to, I expected it to be equal to 36,000 kilojoules, because I know from B to C, that process delta U is at constant volume. So that means the only way of changing energy of the system was through heat, because W is equal to 0. This is an isochoric process. Okay, volume is constant. This one, P, is constant. There's a difference between the two. So this one, we found it to be negative 36,000 kilojoules. Okay, and in the process going from C back to A, in that case, we found delta U is equal to 0 because the temperature is constant. Since the temperature is constant, there is no change in the energy, so W is equal to 0. And delta U is equal to 0, I'm sorry. W is not equal to 0. Actually, W is a finite value in this case, okay? It's a positive value, and Q is a negative value. The reason why I'm saying this one better be 36 kilojoules is because I know in going back from A to A, starting from A but through this entire cycle and coming back to A, the energy should not change because it's state variable. So in other words, the U at A minus the U at A is going to be 0 no matter what U of A is, okay? So this is not true, by the way, for the heat and the work. Heat and work are not state variables. So the heat, there is no such a thing called heat at point A or work at point A. Work and heat depend on the path, okay? So WAB better be 24,000 because I know this one is 60 kg. So this one better be 24 kg with a negative value, because if I subtract this 2, I find 36. So how can I find WAB? Remember, this process is a constant pressure, so this is an isobaric process. So the work is equal to minus the pressure at point A or B, it's the same pressure, it doesn't matter, times the volume at B minus the volume at A. And the volume at B, and so the pressure we found it to be minus 8 times 10 to the power 5 Pascal, times the volume of point B is 0.04, minus the volume at point A, which is 0.01, and this is 0.03 cubic meter. Okay, if I multiply this, 3 times 8 is 24, and 10 times negative 2 times 10 to the power 5, it's 10 to the power 3. And so this is exactly what I needed. WAB is equal to negative 24 kg. So it's exactly what the doctor ordered for us. So if I add this number to 60,000 kg, I indeed find 36,000 kg. So the net change in the energy going from A to A is 0. Okay, and that's important because we wanted to know the change in energy. I think that's the last question of this problem, whether this energy is increased. So yeah, okay, the energy increased from A to B because it went from a temperature of 296 Kelvin from A, which was the point A, starting point A. So this point was 296 Kelvin. This entire line is actually 296 Kelvin, and this line was 1184 Kelvin. So this is a hotter temperature. So the temperature has increased in here. I mean, the energy of the system has increased. And sure enough, it increased by 36,000 kg. And going from 1,184 K to down to 296 through this isochoric process, the energy went down. And sure enough, it went down by negative 36 kg. Okay, and going from C to A, the energy should not change because the temperature is the same. This is an isothermal process. I know I'm repeating myself, but I'm hoping that you guys see this problem because this is a typical problem that you guys should understand. Okay, one of the questions that probably you could ask is, so by the way, delta U going from A to A through this process, this cycle, these three processes basically, should be 0. And sure enough, it's equal to 36 kg minus 36 kg plus 0. This is the portion AB, this is the portion BC, and this is the portion CA, is equal to 0. Okay, so that's exactly what we mean by it. So here is the situation. We take 60,000 during the process when we're warming the gas from 296 Kelvin to 1184 Kelvin. So we took that much heat from it, and the heat was 60,000 kg. During the process, when we were decompressing it at constant volume, in this case, we lost 36,000 kg. So we dumped heat at that point by 36,000 kg. Furthermore, we dumped also more heat during the process where we changed the volume at constant temperature from 0.04 cubic meter down to 0.03, and that was 11,000 kg. So overall, we dumped negative 47,000 kg to the cold source. Okay, so we're operating between the 1,184 Kelvin and 296. So that's how much heat we dumped in the process. Okay, negative 47,000 kg. That's how much heat we took from it. Overall, the work that we did was actually, the net work should be equal to 60,000 kg at with this temperature, this heat, which is negative 47 kg. So this is 13 kg. So how efficient this engine is, and I know we did, if it's an engine operating between in this cycle, so if it's operating between 296K and 1184K, this would have an efficiency of how much? The net work, that's how much we gained from it, divided by the net heat that we took from the hot source, 60,000 kg, and that efficiency. I know this concept, we're going to cover it next chapter, but I'm trying to cover in here such a case. This problem happened to be in an exam or something. So 13 divided by 60 gives me efficiency of 13 divided by 60, 22%. okay? So the efficiency of about 21.6 or 22%, okay? So that's how efficient this engine is. Had this been a Carnot cycle, and we're going to cover this idea later on, okay? It's going to have an efficiency of 1 minus 296 over, which is the temperature, divided by the hotter temperature, which is 1,184, had it been a Carnot cycle. And I'm not saying it is, okay? So had it been a Carnot cycle, its efficiency will be, let's do the math quickly here. I'm trusting, and this is question number 3, by the way, of the discussion today, is that you guys are going to verify all of this math, the numbers that I'm putting for this problem. This would be 3/4, which is 75%. This is a Carnot. Had it been a Carnot engine, this is not a Carnot engine. This engine is isobaric, isochoric, and then isothermal. Carnot engine is a different cycle. Carnot engine would have been more efficient than this one. Okay, Carnot engine would have been 75% efficient versus this engine, which is at 22% efficiency. Okay, in other words, you take 60,000 joules from the hot source, and all you gain from it is only 13,000 joules of work, of net work, which is this area, by the way. Okay, this area, the shaded area between this entire cycle. So it seems to me like this is not a good engine as compared to a Carnot cycle, which is part of the next chapter. Anyway, this is problem 38, and I know I did it in extensive discussion in here. Let's discuss now problem 39 a little bit, probably faster than problem 38. So problem 39, let me draw the diagram because now this one has no data in it, so it's going to be symbolic manipulation, I guess, for the most part, except, no, there are some data in it, but not at least on the diagram. So we have the volume, we have the pressure, we have the starting point, which is called A, and then we go to point B in here in the opposite direction in here via C. So we can go at constant volume to point C, and then at constant pressure to point B. Okay, so this is one way of reaching B in the PV diagram. Also, what we can do here, at least is given to us, another option is to go from A back to point D now at constant pressure, and then from D to B at constant volume. So these are different processes basically taking us back to B. And then at least in the diagram, they show us another kind of not named basically process, doesn't have a name, where we go back from B to A, okay? So this is basically what the diagram on problem 38, by the way, so that you guys look at it, okay? And then it says in here, when a system is taken from point A to B, as in the figure, a long path is ACB. So the path that we're going to go is ACB. During this path, basically, what they're giving us in this case is that Q equals to 90 joules flows into the system. So Q is positive. You have to know, when something is added to the system, that means it adds to the energy of the system. So it's going to be positive in this case, and it's a positive 90 joules. Okay, I'm ignoring the sig figs for right now. Okay, and then 60 joules of work is done by the system. So that means W is equal to negative 60 joules because it's done by the system. So it's not adding to the system. It has to come from somewhere. It has to come from the system. So W in this process from A, C, B. So there is no W in here from A to C. All the W is actually occurring between C and B. But there is definitely heat because I expect this isothermal in here, TA, to be less than TC, which probably is less than TB. So there is heat in here going from A to B, from A to C, and there is definitely also heat involved gained during from C to B. So that total heat is given to be 90 joules. So we don't know how much portion it is, okay? And that's not important at this point, okay? And so the question is, how much heat flows into the system along the path A, D, B? If the work done by the system is 15 kilojoules. Okay, from A, D, B now, the work done by the system is equal to negative 15 joules. They tell you it's done by the system. So if you read the question again, it says you if the work done by the system is 15 joules. They want to know how much heat is in this section in here. So this is Q through this cycle in here, but we want to know Q from ADB, okay? If we know that the work in this case, there is work definitely going from here to from A to B, A to D, because the gas is expanding, so it's doing work because I expect this volume to be higher than this volume. So that's where the negative 15 joules is spent. But how much heat is going to be added also? Because I expect TA to be less than TD, so definitely this temperature is higher than TD, which is less than TB. So there is definitely a Q, so I want to know what that Q is. Well, I know that the change in the energy in the first cycle, this is ACB, is equal to Q plus W. And I know what Q is. It's 90 joules. I know what W is. It's negative 60 joules. So this is a positive 30 joules. So in heating the gas from TA to TB, that requires 30 joules, no matter which way you go through it, because the energy is a state variable. It's a very important concept. Energy is a state variable, meaning it doesn't matter which way you go from A to B, you always need 30 joules to get it there in terms of energy, not work, not heat. That's path dependent. Work and heat are path dependent, whereas the energy is not. So since we go from A to B via C, we can go to it via D, and we still need 30 joules. So for the path ADB now, delta U, which must be 30 joules according to this argument in here, must be equal to the Q plus W. Well, I know how much W they said. It's negative 15 joules. So how much do I need in order to make 30 joules? That requires for me, and move negative to the other side, becomes positive. Q is 45 joules. So in this path, the energy, the heat is 45 joules, whereas in the first one was twice as much. So if we go this way, it's 90 joules, whereas this way it's only 45 joules. In this case, the work was 60 joules in here that the gas has to do, okay? But in this case, the work only is 15 joules, okay? So you see, these things matter, okay? It's very easy to see why the work is different. This is at higher pressure. The change in volume is the same thing. At constant pressure, it's P times delta V, no matter which way you do it. This is P times delta V. Delta V is the same. It's this volume minus this volume, which is this volume minus that volume. Since the pressure in here is less than the pressure in there, so there is more work in here than in here. The gas needs to do more work in here and there and here. Sure enough, this is a negative 60 joules, whereas this one is a negative 15 joules, okay? So you see, this stuff in here is very important, and it's really connected to one another, so please pay attention to these things. So we answered the question. How much heat? The question was, well, it's 45 joules, okay? Okay. And what's the second? When the system is returned back from B to A along the curved path, the absolute value of the work done by the system is 35 joules. Does the system absorb or liberate heat? How much heat is added to it? Okay, so along the path, the curved path, namely from this path, B to A. Okay, so this is path 3 now. Okay, so I'm going to call it 3 in here because it doesn't have a name. Okay. The absolute value of the work done by the gas system is 35 joules. Okay, they tell you the absolute value of the work is 35 joules. Okay, this work better be positive. The reason why it has to be positive is because we're compressing the gas in this case. We're taking it from this volume to this volume. So it's actually in magnitude also, I mean, not in magnitude, the algebraic value is positive 35 joules. That's how much it has to be, okay? Whereas the energy of the system, again, from B to A is just minus this 30 joules, because when we took it from A to B, we needed 30 joules, whichever path we take. If we take it back from B to A, it's just minus the value that takes it from A to B. So delta U in this cycle must be equal to negative 30 joules. So the question is, how much heat? Well, this is still Q plus W. And so Q in this case, so the Q in this case is equal to, I need to make sure that the algebra, it's going to be negative 65, basically Q is equal to negative 30 minus 35, is negative 65 joules, okay? So we're extracting heat. We're taking it from a high temperature to a low temperature. So we definitely are taking heat. So Q must be a negative number in this case. It cannot be positive. So we're cooling it down. So the Q has to be negative in this case, okay? And we're compressing it by, that means that we're doing gas again, we're doing work against it, and W is equal to minus P times the change in volume integrated over this path, which was not given to me. But I know the answer is going to be positive, because at least in an elementary change, the work dW better be minus this number. So this is negative, because we're going from a higher volume to a negative times the negative, so it's going to be positive. So I know it's going to be a positive value, so it's a positive 35 joules. So the answer is, and the change in the energy going from B to A is minus what it takes it to go from A to B. Since it was positive 30 joules, now it's minus 30 joules. So in other words, if I go from A somehow back to B and somehow come back to A, there is no net change in the energy. And because it took me 30 joules to go up to whichever path I come back to, I have to spend that 30 joules back again, so that at the end there is no change in the energy. So in this case, the question is, does the system absorb or liberate heat? In this case, it's going to liberate heat. And this is how much it's going to liberate, okay? How much heat? Yeah, it's 65 joules. If UA is equal to 0 and UD is equal to 8 joules, find the heat absorbed in the process from AD to DB. Okay. They say, and again, this is something that that's part of the discussions that you guys did way back in Physics 1, basically, and that is when you argue the origin of the potential energy and so on and so forth, that it's really what matters is just the difference in it. So they gave you in here, just take UA to be 0 joules, okay? So if UA is 0 joules, they give you also UD is equal to 8 joules. So delta U from A to D is equal to 8 joules, because 8 minus 0 is 8, okay? And they want to know, find the heat absorbed in the process from AD and DB. Okay, that's one thing. Well, we know in this process in here, W is equal to, how much? Is equal to negative 15 joules. The reason why I know that is because they tell you in ADB it's negative 15 joules. And there is only W here. There is no W in an isochoric process. So there is only W in here. So W is given in here. We know delta U. So we can find that delta U is equal to Q plus W, and Q minus 15. That gives me Q equals to negative 15 plus 8. When I move negative to the other side, it's going to be positive. So it's going to be 23 joules, okay? 8 plus 15 is 23, yes, 23 joules. So this is Q between AD, okay? So that's how much it's going to heat up. And it has to be a positive number because you're going from a lower temperature to a higher temperature. And then from dB, okay? Since we know basically the entire Q now, was it given to us? Did we find it? Q from Was it 45 joules? So we know Q, the entire Q from here all the way to B, and we know this portion, we know that, so we can find what the Q is. So the Q is going to be equal to 45 joules minus 23 joules, so it's going to be 22 joules, okay? It's very, I mean, straightforward. Actually, you can use the energy for it too. The energy from A to D is equal to 8 joules, okay? So what you're left with is the energy from B to A, D, which is just Q in this case, because there is W is equal to 0 in this section in here, because it's an isochoric process. So this is 30. That's the entire path from here is 30 joules, because this is 0 now. So this is 30. And from here to here, they tell you specifically this is 8 joules. So if this is 8 joules, this is 30. So 30 minus 8 is 22 joules. So this is 22 joules. So you have two different arguments for the same answer. So that's how you check your answers, okay? Of course, the interesting extension of this question, so that's question 4 of the day if you're not paying attention, okay? Question 4. If this were a cycle, okay, let's take it QCBA, okay, Q, A, C, B, and 3. 3 meaning this path, okay? If this were a cycle, find the efficiency of this engine. Okay, let's think about it in here. Okay, so we know basically how much, so basically we're trying to find this area. Okay, that's all there is to it. So let's find this work in here. So we know during this process, from here to here, we know the Q is 90 joules. Okay, that's correct. And we know during this cycle, the Q is equal to, when we dumped heat through cycle 3, is 65 joules. So this was 90 joules of heat, okay? And this was 65 joules dispensed during the process from here to here, okay? So how much work, net work? W net is going to be equal to 90 minus 65, which is equal to, what is it, 25? Yeah, 25 joules, okay? So if I'm trying to find the efficiency of this engine, it's going to be 25 joules divided by 90 joules, and that should be equal to more than 25%, actually. 25 divided by 90. So it's about 28%. Okay? So that's the answer to the question. So in other words, you can always think of this one as an engine. Okay? If I go from AC to B, and then come back through here, this cycle, that's an engine. Okay, you have to be very careful in here. If I do it this way, if I go from A to B, D to B, and then come back through this path, the energy is going to be different, okay? It's going to be actually not an engine, but rather a refrigerator. That's a discussion. We're going to leave it for next chapter. But at least question 4 has to do with this efficiency, which is 28%, which hopefully you guys would have picked up on it, okay? So that's all I want to talk about problem 38. Problem now 16. Problem 60 is an all data problem, so I'm going to do quickly what this problem look like, okay? So let me get the, let me stop this thing in here, and I'm going to start another one because that requires a screen capture. Okay, welcome for the last problem basically that we still have to discuss is problem 60 from this chapter. As I promised, this problem is all data problem. If you look at the problem, basically, let me read the first part of the problem because it's very important that we need to understand the context where this experiment was conducted. So So it says in here, you compress a gas in an insulated cylinder. What that insulated mean, actually they give you an explanation for it, is no heat flows into or out of the gas. So we know that the process is an adiabatic process. So what they do in this case, they basically vary the volume, they compress the volume from 2.5 liters all the way down to half a liter. So basically, while keeping no heat basically is flowing against the outside of the gas or into the gas. Basically, so what we're doing in here, we're doing work against the gas. So we're adding energy to it. So we would expect the temperature to increase because the internal energy of the system, or the energy of the system, will ultimately increase. The pressure in this case also varies from, of course, we're compressing it, so we're going to increase its pressure from 1/10 of an atmospheric pressure all the way to almost a full atmospheric pressure. So the first question was to basically plot the log of the volume, the log of the pressure versus the log of the volume. In other words, the volume is actually the independent variable, and the dependent variable in this case is the pressure. I did convert in here to SI units. I know that the 1 liter is thousands of a cubic meter, so I divided by 1,000 these numbers, and I took the log. I took the natural log because I think the problem asked to specifically do the natural log, although you could work with the ln and it's going to give you identical results, so it doesn't matter. And I also converted the pressure into a Pascal in here. They gave you the pressure into a atmospheric pressure. We could have used liters and atmospheric pressures and find the value of R that corresponds to those units, but I'd like to stick with the SI units because once we're consistent and we know those numbers, 8.314, so we're good. Okay, so everything is going to work out in SI, the temperature is going to be in Kelvin, the energy is going to be in Joule, and everybody's going to be happy. So I converted this one to, again, Pascal. We know atmospheric pressure is 101,300 basically pascals, but since we have 3 sig figs, I just kept 3 sig figs in the conversion in here times 10 to the power 5, and of course we took the log. So these are the data in here. If you're you should be able to reproduce this data with whatever Excel form. I know I did the first problem, at least from the previous chapter, using GeoGebra, but this is a different way of doing the same thing with Excel, so I really want you guys to be also familiar with this one in here. Anyway, so plotting the function, here is basically the plot. All you have to do is just go into Excel and insert a plot. I took, I think, this one, the first one that came to mind, and I moved it to its own basically sheet, which is called the chart in this case. And what I am after is actually the trend line. So if you click on the graph and you add the trend line, make sure you add the linear trend line. And I actually put more options in here to find the basically the regression analysis, how well fit with the line in this one, and it's almost a perfect line because 99.94% of basically of matching is a pretty good indication that it's a line. Part of the question actually is that why is it so? Why is it linear? So again, because the process is supposed to be adiabatic, because of the fact that this is a process where the heat, there is no exchange of heat, we arrived in lecture to this formula: P times V to the power gamma is constant. How can we find this constant? Basically, all you have to do is just go to a point on the PV diagram and basically make sure that this expression is correct there. So it's going to be one of these points, one of these pressures, times one of this volume, of course, properly converted to the SI units, to the power gamma. At this point, we don't know what gamma is. That's actually part of the whole problem, is to find what gamma is. But the point being in here is this is an adiabatic process, so it obeys this law. And then if I take the log, it doesn't matter which one I take, it's going to give me this linear expression between the log of P and the log of V, equals to a log of another constant, which is just another constant. Okay, so we don't care about this thing in here, it's just a log of this constant. So these two constants are not the same. Anyway, since we're going to take the independent variable in this case being the log of V, and we're going to take the dependent variable as being the log of P, so then if we write this expression, then this will become a y equals to negative gamma times x plus y naught. Gamma is a characteristic of the gas, which is a constant in this case. So it has to be linear in this logarithmic scale. So that's the answer to it, because the process is adiabatic process, and if we use a logarithmic scale on this expression, it's going to be a linear function, and it is indeed with a 99.94% accuracy in here. If you're curious again on how to find these values, all you have to do is go to more options and you pick the display equation, and also display the R value. If I do it one more time, it's going to display me another one which is going to be identical. So that's basically what that is. So I'm going to remove that because I already did it, and I formatted it so that it's going to look big. Anyway, the coefficient in here, it has to be negative, as I said before, as we argued based on this expression here, which is fine. And the number wise is actually the gamma itself. Now, part of the question they ask is this a monoatomic, diatomic, or polyatomic gas? Well, we know it's diatomic because gamma is 1.39, and we know for diatomic gases it's always 1.4. So if you're trying to pick how much this value is, so all you have to do is find the percentage error between these two numbers. So 1.4 minus 1.39, which is 0.01, divided by the well-known value, which is 1.4. So almost 1% error. So this number is actually already, so if I don't multiply it by 100 and leave it as is, you see that this is less than 1% error. So in other words, where is that thing there? Format number in here. Yeah. So this is basically within a 1% error. This is a diatomic gas. So this error in here, this experiment in here is telling me that the gas I am dealing with has two, for example, it's oxygen or nitrogen or something. Okay. So basically that's the type of gas that we're dealing with in this case. So it's a diatomic gas. So that's how we know that, is because the value of gamma from this fit function is 1.4, or very close from 1.4. Please ignore the 2.5 in here. It doesn't mean anything in this case because Excel usually tend to give you more numbers than what you need because of the fact that it doesn't round, or it doesn't know where you're going to round, so it's going to give you extra numbers more than necessary in here, and the sig fix in this one clearly is 3. So I should not really read into it more than 1.39. So these two numbers don't mean anything, they're extra numbers. Okay, anyway, so the question after that asks for basically to find the temperatures, knowing that for P1, namely for 2.5 liters and the pressure of 0.10, basically a tenth of an atmospheric pressure, we know the temperature was basically 22 degrees Celsius. That is room temperature. So we want to know the temperature when we reach the second point in here, namely the volume has dropped by half a liter, and then when it dropped by another half a liter, how much temperature, when it dropped by another half a liter, how much temperature, and we finally dropped to exactly half a liter because it started 2.5 liters down to half a liter. So how much temperature? Well, if you do the formula for, first of all, you need the number of moles, because you know this point. You know the temperature, it's given to be 22 degrees. So what you do in this case, you use this formula, PV equal to nRT for that point. You have the pressure 2.5, you have the volume, which is, the pressure is 0.10, and the volume, which is 2.5. Make sure they are converted to SI if you're going to use a value of 8.314 for the constant, the gas constant in here, times the temperature. The temperature has to be converted to Kelvin. In other words, it's 273 plus 22, that's 296. You plug in these numbers in here, and so this is the formula I've used. Basically, B2 is just this volume. B2 is actually this pressure, it's the blue one, converted to SI, converted to Pascal, and the volume, which is the red one, which is 2.5 in here, divided by 1000, or multiplied by 10 to the negative 3, divided by R, which is this number in here, the times in the denominator the temperature, which is 22 degrees plus 273. I properly formatted just to keep the sig figs in order in here. So the number of moles is actually 100th of a mole. So it's not even a mole, I mean not even half a mole, so which is small quantity. So that justifies in a sense PV equal to nRT. Remember, we're dealing with an ideal gas, so those gases, they have to really have a small number, unlike one of the problems we did previously, which has a 3 moles, which is really where we have to be careful whether or not PV equal to nRT applies correctly, or we need to make corrections to it, because there will be more molecules in that gas, so there is a possibility for internal collisions between them other than just colliding with the walls. So we really needed to correct that law if we really needed to have more moles. So this is a good enough approximation, actually. That's good. Okay, so now we have to find the temperatures for each and every one of the other 2 points in here. So we go back into PV equal to nRT now, since we know N, and basically I just made a switch in here, converting with this N in here using this formula, so that actually I don't use N, but use this formula for the temperature that is 22 degrees, but properly converted. You have to add to it 270 to make it 296, and then multiply it by the pressure in here, the volume in here, divided by the pressure in here, and the volume in here, and deduct 273 if you expect this number back to degrees Celsius, as it's clearly asked in here. So anyway, use this formula in here if you're curious about the math in here. So this is given, but this is basically the same formula as I was talking about in here, making sure that the denominator doesn't change. That's why you see the dollar symbol in here. Excel is something that you guys need to know if you're going to be a successful engineer. So this is something that you have to use. I was tempted to give you this file, but I expect you guys to master the skills, and we will have a lot of problems down the road, and also labs, so that you guys practice it more. So exam time, if you don't have access to it, it's something that you should be able to get for free as students. If not, use GeoGebra, and we could have done the same calculations in GeoGebra and would have gotten the same thing. As a matter of fact, I started with GeoGebra, but then I thought that maybe we should do something different so that you guys make sure that you know Excel, because everybody expects you to know Excel. Anyway, we calculate the temperatures and we see that it's increasing. Sure enough, we compress the gas with no heat exchange, so we're adding energy to it. That is translated in temperature, period, end of the story. We didn't heat it, we didn't put it into the furnace, so it gets hotter and hotter by virtue of the fact that we're compressing it. Okay, we're doing work against it, so we're adding to its internal energy. So the temperature increases, and that's the question. It's asking you to calculate the temperatures and explain why it's going to be increasing. Well, the internal energy of the system is increasing. It reaches 283 degrees Celsius, so this is very, very high temperature. We started at room temperature, we're almost at 300 degrees Celsius, which is super hot temperature. Anyway, this is basically in a nutshell what your problem is. And if you guys have any questions, please do ask. And that's it. So I'm gonna stop the recording now.